Welcome to another deep dive. You know how this works. You send us something you want to really understand, and, well, we do our best to unpack it.
That's right. Break it down and make sure we both really get it.
Exactly. And today we're tackling a chapter someone sent in called Particle Physics and Cosmology. Wow. So it's a pretty ambitious deep dive. We're talking about literally everything.
Yeah, from the absolute smallest stuff we know about to the biggest in the entire universe.
So where do we even start with something like this? I mean, it's a pretty dense chapter, lots of theories and historical stuff, definitions. How do we even approach this?
Well, I think the best way to make sense of all this is to follow the journey, right? Like, how did we even come to understand these fundamental particles in the first place?
Okay, so like a historical perspective.
Yeah. And then we can see how that led to our current picture of the universe and all the amazing stuff in between.
I'm in. Let's do it.
All right. So let's rewind all the way back to the ancient Greeks.
Boy,
Yeah.
here we go. Philosophy time.
Well, they had this idea about atoms. You know, these tiny, indivisible particles that make up everything?
Right, like the most fundamental building blocks.
Exactly. And that idea stuck around for centuries. But it wasn't until much later in the late 1800s that things really started to heat up.
Yeah, I remember learning about this in school, like the discovery of the electron, right?
Exactly. J.J. Thomson, 1897. He showed that atoms weren't indivisible after all. They had these tiny, negatively charged particles inside them. Electrons.
Okay, so atoms weren't the end of the story.
Not even close. Then a few years later, Ernest Rutherford comes along and blows everyone's minds.
Okay, how so?
So he's doing these experiments, firing alpha particles at gold foil, and most of them pass right through, but a tiny fraction bounce back.
So like something's in there.
Yeah, some dense, positively charged core that he called the nucleus.
And that's where the proton lives, right?
Right. The proton positively charged hanging out in the nucleus. So now we've got electrons and protons. We're starting to build a picture of the atom.
It feels like we're on a roll here. But then things get a little weird with Einstein.
Yes, Einstein always shaking things up.
So he comes along with this idea of the photon, which isn't really a particle in the same way as an electron or a proton, is it?
It's a different beast altogether. So Einstein's looking at this thing called the photoelectric effect.
Right. Light shining on a metal can cause electrons to be emitted.
Yeah. And the classical theory of light as a wave couldn't explain this, but Einstein proposed that light also exists as these discrete packets of energy, photons.
Okay, so light is both a wave and a particle.
In a way, yes. It has this dual nature.
So now we've got electrons, protons, and these weird photons. What's next in this particle party?
Okay, so back to the nucleus. We've got all these positively charged protons crammed together.
Seems like they'd want to repel each other.
They should. And that's where the strong nuclear force comes in. There had to be some incredibly strong force holding them together.
But what's responsible for that force?
Enter James Chadwick, 1932. He discovers the neutron, a neutral particle with about the same mass as a proton.
Okay, so the neutron is the peacemaker in the nucleus.
Exactly. It adds to the strong force without adding to the electromagnetic repulsion.
So we've got our fundamental trio then. Electron, proton, neutron. Are we done?
Not even close. This is where things get really interesting.
Yeah, but what's next?
In 1932, Carl Anderson discovers the positron.
What's that?
It's the antiparticle of the electron. Same mass, but opposite charge.
Antimatter. Like something out of Star Trek.
It was a huge deal. This discovery confirmed Dirac's theory of antimatter. It's like a mirror image of the particle world.
So for every particle, there's an antiparticle.
Exactly. And when a particle and its antiparticle meet, they annihilate each other, releasing a burst of energy.
That is so wild. And you're telling me this isn't even the weirdest part.
Just wait, we're just getting started.
Okay, so we've got all these particles. But how do they interact with each other? It's not like they're just floating around randomly.
Right, that's where the concept of forces comes in, or more precisely, the concept of force carriers.
Force carriers, so like particles that carry the forces.
Exactly. Imagine two people playing catch with a ball. The ball is the mediator of their interaction.
Okay, I can see that.
So similarly, in the quantum world, forces are mediated by the exchange of specific particles. Like, for example, the electromagnetic force is mediated by photons.
Okay, and what about the strong force that's holding the nucleus together? What's its carrier particle?
That's a good question. Back in the 1930s, a physicist named Hideki Yukawa predicted the existence of a particle that would mediate the strong force.
And he called it
the meson. And based on the range of the strong force, he even estimated the meson's mass.
That's impressive.
And it turned out to be pretty accurate, but there was a bit of confusion at first.
How so?
Well, around the same time, they discovered a particle called the muon, and its mass was kind of close to what Yukawa had predicted.
So they thought they'd found the Mason.
Yeah, but it turned out the muon didn't interact with nuclei the way a strong force mediator should. So it was a bit of a dead end.
So the search continued.
It did.
Yeah.
And eventually they found the real deal, the pion. Its mass and its strong interaction with nuclei matched Yukawa's predictions perfectly.
So the pion is the glue that holds the nucleus together. Amazing how all these pieces fit together.
It really is. But to really study these particles and their interactions, we need some serious firepower.
Firepower, what do you mean?
I'm talking about particle accelerators.
Ah, yes. Those giant machines that smash particles together.
Exactly. These things use electric and magnetic fields to accelerate charged particles to incredibly high speeds, almost the speed of light.
So we can see what happens when they collide.
Right. The higher the energy, the more we can probe the fundamental nature of matter.
And we've got different types of accelerators, right? Like linear accelerators or linacs.
Yeah, linacs are basically straight tracks, where particles get accelerated by a series of oscillating electric fields. It's like giving them a series of tiny kicks to boost their energy.
And then there are cyclotrons.
Cyclotrons use a magnetic field to bend the path of the particles into a spiral. And as they spiral, they get accelerated by an electric field each time they cross a certain gap.
Clever way to keep them contained.
Exactly. But for even higher energies, we need synchrotrons.
Synchrotrons. What's special about them?
Synchrotrons also use magnetic fields to keep the particles in a circular path, but the key is that they can adjust the strength of the magnetic field as the particles gain energy.
So they can reach even higher speeds.
Yep. And that means more energy available for creating new particles when they collide.
Makes sense. And I remember reading that colliding particles head-on is much more efficient than just smashing them into a stationary target. Why is that?
Great question. It's all about available energy. When you have two particles colliding head-on, the total energy of the collision can be used to create new particles.
Whereas with a stationary target, a lot of the energy is wasted just moving the target.
Exactly. So colliding beams are the way to go for high-energy physics.
Okay, so we've accelerated these particles to insane speeds and smashed them together. Now how do we actually see what happens?
That's where particle detectors come in. These are incredibly sophisticated instruments that surround the collision point and capture information about the particles produced in the collisions.
It's like a giant microscopic camera.
In a way, yes. Early detectors like cloud chambers and bubble chambers actually allowed you to see the tracks of the particles.
How'd that work?
Cloud chambers use a supersaturated vapor, and when a charged particle passes through, it ionizes the vapor, creating a trail of tiny droplets that you can actually see.
That's pretty cool. And bubble chambers?
Bubble chambers work similarly, but with a superheated liquid. The particle creates a trail of bubbles as it passes through.
So it's like visualizing the invisible.
Exactly. But modern detectors are much more advanced. They use all sorts of electronic sensors and magnetic fields to track the particles and measure their properties.
Like what kind of properties?
Well, things like their charge, momentum, energy, and even what type of particle it is.
That's incredible. So we've built these huge machines to smash tiny particles together, and then we have these incredibly complex detectors to analyze the debris. It's all very impressive.
It really is. But it's important to remember that we don't always need these giant machines to study high-energy particles.
Oh, right. Cosmic rays.
Exactly. Cosmic rays are high-energy particles that come from space and constantly bombard the Earth.
And some of them have energies far exceeding what we can achieve in our accelerators.
That's right. So cosmic rays provide a natural laboratory for studying high-energy physics.
And for detecting neutrinos, we need to go deep underground, right? Why is that?
Neutrinos are incredibly elusive. They interact so weakly with matter that they can pass through the entire Earth without even noticing.
So we need a lot of shielding to block out other particles and just look for those rare neutrino interactions.
Exactly. That's why neutrino detectors are often located deep underground in mines or under mountains.
It's amazing how far we've come in our ability to study these particles. But now I want to step back and talk about the forces themselves. You mentioned 4 fundamental forces of nature. What are they?
Okay, so in order of decreasing strength, we have the strong force, the electromagnetic force, the weak force, and the gravitational force.
And each force has its own set of carrier particles, right?
You got it. The strong force is mediated by gluons. the electromagnetic force by photons, the weak force by W and Z bosons, and gravity is thought to be mediated by a hypothetical particle called the graviton.
Hypothetical. So we haven't actually found it yet.
Not yet. The graviton is proving to be very elusive.
I can imagine. Okay, so not all particles experience all these forces, right? That's where leptons and hadrons come in.
Exactly. Leptons, like electrons, muons, and neutrinos, don't feel the strong force. They only interact via the weak force, the electromagnetic force, and gravity.
And hadrons.
Hadrons are the particles that do feel the strong force, like protons and neutrons.
And we also classify particles based on their spin, right? Fermions and bosons. What's the difference?
So spin is a fundamental property of particles. It's a kind of intrinsic angular momentum. And fermions have half-integer spin, like 1/2, 3/2, and so on, while bosons have integer spin 0, 1, 2, and so on.
And this difference in spin actually affects how they behave.
Big time. For example, fermions obey the Pauli exclusion principle, which basically says that no two identical fermions can occupy the same quantum state.
So like they can't be in the same place at the same time doing the same thing.
Exactly. And this is super important for the structure of atoms and matter in general. Bosons, on the other hand, don't care about the Pauli exclusion principle. They can pile on top of each other in the same state.
Interesting. So it's all about the spin. Okay, so now that we've got all these particles and forces, are there any rules that govern how they interact?
There are several important conservation laws. For example, energy and momentum are always conserved in any particle interaction.
That makes sense. Those are like fundamental laws of physics.
Exactly. And then there are other conservation laws that apply specifically to certain types of particles.
Like what?
Well, for example, there's lepton number, which is conserved in all interactions involving leptons. And there's baryon number, which is conserved in interactions involving baryons.
Okay, so these conservation laws basically limit what kind of reactions can occur.
Exactly. They're like the traffic cops of the particle world.
I like that.
Yeah.
And the chapter also mentions this thing called strangeness. What is that all about?
Strangeness is a quantum number associated with the specific type of quark called the strange quark. And it's conserved in strong and electromagnetic interactions, but not in weak interactions.
Okay, that's a bit much for me.
Basically, it was introduced to explain why some particles seem to decay more slowly than expected. They had this property called strangeness that had to be conserved in certain interactions.
Okay, so it's another one of those quantum rules that govern the particle world.
Exactly. It's all about understanding the patterns and symmetries in the way particles behave.
I'm starting to see that. Okay, so now we're ready to delve even deeper into the structure of matter. We know that hadrons, like protons and neutrons, are made up of even smaller particles called quarks.
Right. The quark model was a major breakthrough in particle physics.
The quarks are like the ultimate building blocks.
As far as we know, yes. And there are 6 different flavors of quarks: up, down, charm, strange, top, and bottom.
Flavors, like ice cream.
Not quite. It's just a way of distinguishing the different types of quarks. They all have different properties like charge and mass.
And these quarks are held together by the strong force right. But what's mediating that force at the quark level?
Gluons. Gluons are the force carriers of the strong force. They're constantly being exchanged between quarks, holding them together.
So gluons are like the super glue of the particle world.
That's a good analogy. But gluons are even weirder than regular glue. They actually carry a property called color charge.
Color charge. So quarks are actually colored?
No, it's not
Yeah.
the same as the colors we see. It's just an analogy. There are 3 colored charges: red, green, and blue, and their corresponding anticolors.
Okay, so it's like a different kind of charge. Not electrical charge, but color charge.
Exactly. And quarks can't exist in isolation. They always have to be bound together in combinations that have a net color charge of white.
Like mixing red, green, and blue light to get white light?
Exactly. And the theory that describes all this, the interactions between quarks and gluons, is called quantum chromodynamics, or QCD.
QCD. Sounds intense.
It is. It's a very complex theory, but it's been incredibly successful in explaining the behavior of quarks and the strong force.
So quarks, gluons, color charge, QCD. We're really getting down to the nitty-gritty here.
We are. But it's amazing how all these pieces fit together.
So this brings us to the standard model of particle physics. What exactly is the standard model?
The standard model is our best current theory, describing all the known fundamental particles and their interactions via the strong force, the weak force, and the electromagnetic force.
So it's like the ultimate periodic table of the universe.
You could say that. It's a remarkably successful theory that has been tested and confirmed by countless experiments.
And it includes all the particles we've talked about so far, right? Quarks, leptons, force carriers.
Yes, all
Uh-huh.
of them. And it also incorporates something called the electroweak theory, which unifies the weak force and the electromagnetic force at high energies.
Unifies them. So those two forces are actually different aspects of the same force.
That's right. It's a bit like how electricity and magnetism are different manifestations of the same fundamental force.
And the Standard Model also includes the Higgs boson, right? What's that all about?
Ah, the Higgs boson. That's the particle associated with the Higgs field, which is responsible for giving particles their mass.
Okay, hold on. Explain that one a little more
Mhm.
slowly.
Imagine a swimming pool full of water. The water is like the Higgs field, and particles moving through this field experience a kind of resistance.
So like the more resistance they experience, the more massive they are.
Exactly. And the Higgs boson is like a ripple in this field. It's the particle that we actually detect.
And they actually found the Higgs boson at the Large Hadron Collider a few years ago, right?
It was a huge discovery confirming a key prediction of the Standard Model.
So the Standard Model is pretty much the end of the story then. We figured it all out.
Well, not quite. There are still some big unanswered questions. For example, the Standard Model doesn't include gravity.
Right. That's always the odd one out.
It is. And there are other mysteries too, like why neutrinos have mass and what dark matter and dark energy are made of.
So there's still plenty of work to be done.
Oh, definitely. Physicists are always looking for ways to go beyond the Standard Model to try to answer these big questions.
Like what kind of ways?
Well, there are ideas like grand unified theories or GUTs, which try to unify the strong force, the weak force, and the electromagnetic force into a single force.
Ambitious.
It is. And then there are even more speculative ideas like supersymmetry and string theory, which try to incorporate gravity into the picture and maybe even explain the origin of the universe.
So the quest for a unified theory of everything continues.
It does, and it's a fascinating journey. But for now, let's shift gears and talk about the universe as a whole.
Okay, so from particles to cosmology.
Mm-hmm.
How did we get here?
Well, in the early 20th century, astronomers started noticing something strange about the light coming from distant galaxies.
What was strange?
The light was redshifted, meaning the wavelengths were stretched towards the red end of the spectrum.
And this redshift meant that the galaxies were moving away from us.
Exactly, and the farther away the galaxy, the faster it seemed to be receding.
So the universe isn't static, it's expanding.
That's the conclusion Edwin Hubble came to, and he formulated a law that describes this expansion, Hubble's law.
Right. The recession velocity of a galaxy is proportional to its distance from us.
Exactly. And this discovery was revolutionary. It completely changed our understanding of the universe.
And if the universe is expanding, that means it must have been smaller and denser in the past, right?
Precisely. And that led to the development of the Big Bang theory.
The idea that the universe originated from an incredibly hot and dense state about 13.8 billion years ago.
That's right. And it's been expanding and cooling ever since.
So the Big Bang wasn't an explosion in space, but rather an expansion of space itself.
Exactly. It's like the fabric of space itself is stretching.
Mind-blowing. And the redshift we observe is due to this stretching of space, not just the galaxies moving through space.
Precisely. As light travels through this expanding space, its wavelength gets stretched, which shifts it towards the red end of the spectrum.
Okay, that makes sense. So if the universe is expanding, will it keep expanding forever? Or will it eventually stop and collapse back in on itself?
That's a great question. And it depends on the average density of matter and energy in the universe.
So like if there's enough stuff in the universe, gravity will eventually pull it all back together.
Exactly. There's a critical density that determines the fate of the universe.
And what do we think the actual density is compared to this critical density?
Well, based on our current measurements, it seems like the average density is much lower than the critical density.
So the universe will keep expanding forever.
That's what it looks like, but there's a twist.
Okay, I'm intrigued. What's the twist?
It turns out that the expansion of the universe isn't just continuing, it's accelerating.
Accelerating, so things are moving apart faster and faster.
Exactly. And this acceleration is thought to be caused by something called dark energy.
Dark energy. That sounds ominous.
It's a mysterious form of energy that permeates all of space and exerts a negative pressure, causing the expansion to speed up.
So we don't really know what it is, but we can see its effects.
That's right. Dark energy is one of the biggest mysteries in cosmology today.
So the universe is expanding and accelerating. What a wild ride. But what about the very beginning? What can we say about the universe right after the Big Bang?
Well, based on our current understanding, the early universe was an incredibly hot and dense soup of fundamental particles.
Like quarks and leptons zipping around at crazy speeds.
Exactly. And as the universe expanded and cooled, the fundamental forces began to separate or uncouple from each other.
So like the strong force separated from the electroweak force and so on.
More precisely. And there was a brief period called Big Bang nucleosynthesis where protons and neutrons combined to form the light nuclei, like hydrogen and helium.
So the first elements were forged in the fiery crucible of the Big Bang.
That's right. And after about 380,000 years, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms.
And that's when the universe became transparent to light, right? Because the photons were no longer scattering off free electrons.
Exactly. And this released the cosmic microwave background radiation, which is like a snapshot of the universe at that time.
So we can actually observe this radiation today.
We can. And it's one of the strongest pieces of evidence supporting the Big Bang theory.
So we've come a long way from those early observations of redshifted galaxies to a detailed understanding of the universe's evolution.
We have. But there are still many mysteries left to solve.
Like what?
Well, for example, we don't know why there's so much more matter than antimatter in the universe.
That's a big one. If matter and antimatter were created in equal amounts in the Big Bang, they should have annihilated each other, leaving nothing but radiation.
Right. So there must have been some asymmetry, some slight preference for matter over antimatter in the very early universe.
But we don't know what caused that asymmetry.
Not yet. It's one of the most fundamental questions in physics and cosmology.
And then there's dark matter and dark energy. We still don't know what they're made of.
Those are big ones, too. Dark matter makes up about 85% of the matter in the universe, and dark energy makes up about 70% of the total energy density.
So we're basically clueless about 95% of the universe.
Pretty much, but that's what makes cosmology so exciting. There's so much still to discover.
Well, this has been an incredible journey. We've covered everything from the tiniest particles to the vastness of the cosmos.
We have, and we've seen how these two seemingly disparate fields are actually deeply interconnected.
It's amazing to think that the same laws of physics govern both the subatomic world and the evolution of the universe as a whole.
It's a testament to the power and beauty of science.
Where I'm exhausted, but in a good way. Thanks for guiding us through this complex and fascinating material.
It was my pleasure. And who knows what new discoveries await us in the future.
Exactly. Until next time, keep exploring the universe, both big and small.